Hello students, in today's video we will solve a differential equation using Runge method of fourth order. Okay, so first, if this is our differential equation dy by dx equal to f of x y, and this is the initial condition y at x naught is equal to y naught, then yi plus 1 is equal to yi plus y of xi plus h. Okay, and that is equal to yi plus k. So this is a yi plus 1, and here we have to find this k, where formula of k is 1 by 6 times k1 plus 2 times k2 plus 2 times k3 plus k4. What are these ki's here? So here k1 is h times f of xi yi, where f of xi yi will be slope at the beginning of the interval using this y. Now k2 is h times f of xi plus h by 2 comma yi plus k1 by 2. This is slope at the midpoint of the interval, this f of xi plus h by 2 yi plus k1 by 2, using values of y and k1. Then k3, this is a formula for k3, h times f of xi plus h by 2, first term is same here, and yi plus k2 by 2. So this is also slope at the midpoint, but by using value of y and k2. Then k4, this is h times f of xi plus h yi plus k3, and where f of xi plus h yi plus k3 will be slope at the end of the interval. So, and we will take average of this, and in this average we are giving greater weightage to these midpoints. Okay, so this is how we will find average slope, and that will be used to approximate the value. So this is what Runge method. So let us solve one example, and this method gives us very good answer compared to previous methods, that is Euler's method and modified Euler method. And generally this method is used for, so this method is generally used for day-to-day or real life examples while solving real life problems. Okay, so this method is very useful. So let us have this example. We will take this simple example so that we can solve this example using analytic method also, and then we will compare our answer with that method. So dy by dx plus 2xy is equal to x. This is our differential equation, and initial condition is y at 0 is equal to 1. That means when x is equal to 0, y is equal to 1. This is given, and we have to find what is y when x is equal to 1. Okay, so this is our f of xy. F of xy will be x minus 2xy. Then x naught is 0, y naught is 1. Okay, so we will take h is equal to 0.5. So there will be 2 steps, 2 iterations will be there. Now y1 will be, so y at x naught plus h. Okay, so which is y naught plus k, where you have to find k. So this is a formula for k. So let us, this is k1. Okay, so first find k1, which is 0. We will substitute here 1 by 2 x minus 2xy. This is our f of xy at 0 comma 1, because x naught is 0 and y naught is 1. So when you put this, x is equal to 0 and y is equal to 1, we get 0. So k1 is 0. Then find k2. Formula for k2 is h into f of x naught plus h by 2 comma y naught plus k1 by 2. k1 is 0, h is 0.5, x naught is 0, y naught is 1. So you have to find this 1/2 x minus 2xy at this 1 by 4 comma 1. Okay, x naught plus h by 2 will be 1 by 4, and y naught plus k1 by 2 will be 1. So which is minus 1 by 8. Similarly, we will find k3, which is minus 7 upon 64. You can go through these calculations also, or you can solve this example by your own also and check this answer, check these values of ki's. Then k4 will be minus 25 upon 128. So I am taking these values in this rational form, a by b form, so that there will be no rounding of error. Okay, so that we can compare our answer. We will we will get how this method gives, how much accurate answer this method will give us, so that we can check later on. Okay, then k will be minus 85 upon 768, and therefore y1 will be this, because y0 is 1. So 1 minus 85 upon 768 will give us this value, minus 683 upon 786. So y1, that is y at x is equal to 0.5, okay, which is this 0.8893 and this number. Okay, now for y at x is equal to 1, so x1 is equal to 0.5, y1 is this, so y2 will be, so now same formula, only in place of here y1, now we are finding y2, and for that we are taking x1 here. So y1 plus k, again we find value of k. So here k1 will be h times f of x1 y1, this minus 299 upon 1536. Then k2 is this, similarly we will find k3 and k4. So we got all these values, and therefore from this we will get k, which is this. Alright, and when you put this in this equation here, we'll get y2, that is y at x is equal to 1, which is this much, minus 134483 upon 196608, which is this 0.6840159098307929. Okay, so this is what answer we got by RK method or Runge-Kutta method of fourth order by taking h is equal to 0.5. Now let us solve the same example using analytic method. So this is a linear differential equation, you can see, and we will first find its integrating factor, which is e raised to x square, and general solution is this. So when you solve this, so for that we need to use substitution, put x square is equal to t. Okay, and after solving this differential equation, we will get y is equal to 1 by 2 plus c into e raised to minus x square. Now we have to find this value of constant. For that we will use this initial condition, when x is equal to 0, y is equal to 1. So that will give us c is equal to 1 by 2. And therefore this is the particular solution, 1 by 2 times 1 plus e raised to minus x square. Now we are supposed to find value of y at x is equal to 1. So put x is equal to 1 in this equation, or this value of y. We get y at x is equal to 1 as this 0.6839. So why I am taking this, this is after decimal point there are 15 to 16 values. So why I am taking this, so that we can compare it with the Runge-Kutta method. Now see here, so this is actual answer. By Runge-Kutta method, when we take h is equal to 0.5, we got this. So you can see here, this answer is correct up to only 2 decimal places, but we took h is equal to 0.5 only. Now see, when you take h is equal to 0.25, you will get this. Y will be 0.6839 and these numbers. So the answer will be correct up to 4 decimal places. You can see here, when we are taking h is equal to 0.25, answer is correct up to 4 decimal places. If you further reduce value of h, for h is equal to 0.1, we are again getting answer correct up to 4 decimal places, but it is more accurate than this one, because here the 5th decimal place is 3 and here it is 6 and 4. So we are getting more accurate answer as we are reducing value of h. For example, now what if h is equal to 0.05? This will increase our iterations, but look at the accuracy of the answer. Now this is accurate up to how much? 3 and 3, 7 decimal places. If you take h is equal to 0.01, the answer is almost correct up to 9 decimal places. If you take h is equal to 0.001, answer is correct up to how much this? Maybe 15 decimal places, 15 or 14. and when you take h is equal to 0.001, you can see you got exactly same as this. This answer is by using analytic method. You can look here, check here at the top, and now when we take h is equal to 0.0001, we got exactly this answer. So it depends how much accuracy you want. According to that, you have to reduce value of h. Now let us check some of these values using Python program. So we have this Python program here. We will enter our function. So it is x minus 2 times x into y. This is our f of x, right? Now initial values. So what are the initial conditions? When x is equal to 0, y is equal to 1, and you have to find x in, that means at what value of x you have to find y. So at x is equal to 1, let us put value of h. So let us take h is equal to 0.1 first. Okay, in this case, when you put h is equal to 0.1, so it will take 10 iterations and you will get answer as this 0.6839, okay, which you can check with the answer that we have here, 6839. Let us go back and check for 0.001. So let us change this h. What if we take h is equal to 0.001? In this case, it will take 100 iterations. But see, you don't have to do all these calculations in real life. You don't have to do all these calculations by hand. You have such programs. Okay, so it will not take much time. Within seconds, it will give you answer. So for h is equal to 0.001, look at here. What we got here, y will be this 0.683939. Alright, so here is that answer 0.001, which is correct up to 15 decimal places. Alright, so this is how you can solve examples by using Runge Kutta method. And if you want, you can write a Python program or program in any language, because all these methods, numerical methods, are not meant for by hand calculations. Okay, you'll require plenty of calculations, so it will be always very good if you write some program on that. So I hope you understood this method, and this is how this Runge Kutta method works. It is very useful method, and it is extensively used in all type of problems where you have to solve these first order differential equations. And this is the best method we can have, and it is easy also, and it is very efficient method. Thank you.